Kinetic agents. Okay, class. So let's start. Okay, so we'll be continuing with A2. Okay, continuing with A2. So I think we are discussing the halfway of ideal gas, right? Okay, so let's continue. Okay. Okay, so just checking. Hold on. It's on. Okay, guys, just okay. So we're done with the mole. Okay, we're done with the mole concept. Now we're done with the equation of state 2. New formulas was introduced. Okay. Today we're going to go through the third one, kinetic theory of gases. Okay. Okay. So yeah. So we learn about number of moles. Just go through fast. So conversion you have to know. So what is ideal gas? In one single line, I told you, it's a type of gas that obeys the equation of state, the gas laws. PV equals to nRT, and any pressure, temperature, any pressure, volume, and thermodynamic temperature. It's ideal gas. Okay. Yeah, so this all we done. So PV equals to nRT. So we got to know the three Boyle's formula, Charles formula, pressure formulas combined. End up getting which formula? These two, right? Yeah, PV over T is constant. Then skip this. So PV equals to nRT and PV equals to nKT is formed. Okay. Okay, now, so these are some questions about it. Can we skip this? Can you try? Okay, now we're going to talk about kinetic theory of gases. Previously, I told you what causes the pressure by the air particle to the wall is the collision of the air particle. Okay, so scientists want to get a formula involving the speed of the air particle, which doesn't reveal in the early formulas. See the early formulas, PV equals to nRT. We don't know where the speed lies. Okay, the speed of the particle is not there. So they want to get a formula in terms of speed. So which end up giving you this formula. So this today's lesson, how they got this formula. Okay, to get this formula, they did lots of assumption. Kinetic theory of gases. Okay. What scientists, of course, gases we can't see. Naked eye we can't see how the particles are moving. So they did lots of assumption about how the particles are moving in the gases. Okay, there are a few assumptions. Okay, so the first one assumptions: gas consists of large number of molecules. Okay, the molecules are moving, always move very rapidly and randomly. Okay. And the collisions of the particles are said to be perfectly elastic. These all are assumptions made. The duration of collision is negligible compared with the time interval between the collision. That means colliding time is too small compared to time between the collision. Okay. Yeah. So there are no intermolecular attractive force. Okay, this is famous. And finally, the volume of the molecule is negligible compared to the volume of the container. Okay. In exam, they will ask at least 3 for you to write. Write 3 kinetic theory of gases. Three assumptions. Okay. I think the one you can list down is the one neglected first. Okay. The collisions are what do you call the neglected one. The volume of the molecule is neglected compared to volume of the particle or volume of the gas. The intermolecular force is neglected. These are the 2 neglected. Okay. The collisions are perfectly elastic. Okay. So remember, you need to write at least 3 in your exam. Okay. So now based on these assumptions, okay, so this formula was derived. Okay, now let's go for the derivation of this. So based on the kinetic theory, we found that there are air particles trapped into container. This is how they move. They move randomly. They collide to the wall. They exert pressure. Okay. Sorry, yeah. Sorry for the. Hello. Okay. Oh, sorry. Just a call. Okay. Sorry, yeah. Okay, so the collision of the particle causes the pressure. So the derivation start with, I go again brief. So pressure caused by pressure is force over area. What is force? Force is rate of changes of momentum. So what is momentum? Momentum is mass times velocity. Okay. So the derivation of this equation is going to start with momentum. Momentum of the particle we're going to get the force exerted by the particle to the wall. Then finally, we're going to get the pressure formula. This is the road to finding the pressure formula. Rough the 3 steps. Okay. So first, this is the model we're going to follow. There is a box, like a box. You're assuming the surface is like a cube. It's a cube. There is first assuming there is, let's say there is one particle m, move with the speed of cx. Okay, the gas particle has a mass of m, move to the right with the speed of cx. Okay, so we want to find the pressure on the surface of one. We want to find the pressure of the surface of one. Of course, the container contains 6 surfaces. We want to find the pressure at one. So first we get the momentum first. So when this particle go and collide with the first surface, the surface 1, how much the momentum it possess? Of course, mc x. It has a momentum of mcx at x direction. Okay. Now, So at phase 1, we go to phase 1, there is a perfectly elastic collision. So there the momentum is reversed to negative mcx, correct, right? And the particle collide to the wall, it experiences elastic collision. So it's going to bounce back with negative cx, right? To the right, to the left. So therefore, the momentum change experienced by the particle and the wall, okay, both same magnitude, right? So the changes in momentum of the particle is mcx minus mcx, right? Because mcx to the right minus negative mcx. So the total momentum experienced by the particle is 2 mcx. This is the changes in momentum experienced by the particle. This also the same magnitude of changes of momentum also experienced by the wall, right? When two bodies collide, you learn in AS, right? When two bodies collide, both, well, let's say the car collide with the lorry, the car and lorry both will experience the same amount of changes in momentum, right? But in opposite direction. So this is the changes in momentum experienced by the wall and also particle in terms of magnitude. Okay. What do you want to get? You want to get pressure. We want to get pressure. We get the changes in momentum. We get the force, and we get the pressure. Okay, that's how we develop. Okay, so we go back. So one particle experiences 2 mcx. Okay, after colliding, we want to get force now. You see the towards the end of this slide is a force. We want to find a force. Force exerted by the particle to the wall. Okay. For that, after colliding with phase 1, the molecule travel a distance of 2L. Do you agree? Particle travel 2L, right? You see the box? The box length is all L. Length is L, width is L, height is L. It's a cube. So when the particle hits the wall 1, you're going to move to the wall 2, travel a distance of L, and bounces back again, travel a distance of L. You take 2L. You have to travel 2L. Every 2L, you're going to collide with 1. Every 2L. Okay. So after colliding with phase 1, the molecule travel a distance of 2L. Right? Do you agree? It's 2L. Go L and come back again another L to meet 1. Okay. So before it collides with the phase 1. Okay. So the time taken to travel for each collision, that means time taken to travel for each collision is T. T is 2L over Cx, the speed it travel. Okay. This is the time of collision, each collision. Okay. Time interval of each collision. Okay. So you know the momentum change experienced by the particle is 2 mcx. Time of collision is 2L over Cx. So we can find the force exerted by the particle to the wall. Force exerted by the particle to the wall is change in momentum over the time taken for this momentum change to happen. Okay, it means change in momentum 2 mcx over the time taken is 2L over Cx. So we get the force formula. This is the force exerted by only one particle. Only one particle. One particle which has a mass of m, which has a speed of Cx, exert a force of this much, mcx squared over L. Okay. So this is the half way of derivation. You must know how to derive, but I tell you about 12, I think for the past 12 years, not even once the derivation has been asked. Okay. Only as part of the derivation has been asked. So I will tell you which part. Okay. So try to understand the derivation. mcx become 2 mcx. Time taken is 2L over Cx. So force is momentum, total momentum change divided by the time. So this is the force exerted by one particle to the wall 1. Okay. Okay. So now we go for a more realistic model. So the force exerted by the one particle is found to be mcx squared over L. M is the mass of one particle. C is the the horizontal speed of the particle, L is the length of the container. So now we want to find pressure. Of course, focus is to find pressure. The pressure, you know, is force per unit cross-sectional area, right? Force per unit area. So force, just now we know, is mc squared L squared, per over L. The area itself is another L, right? So it's L squared. So the pressure caused by this one particle to the wall of 1 is found to be mc squared over L cube. So this is the pressure caused by what? Only one particle. One particle which traveling horizontally. Okay. So after this, we're going to make the model become more elastic. Okay. After this line. Okay. How do you make it more elastic? Now, of course, the gas not only contained with one particle. It might have lots of particles, right? So let's say, suppose we have n molecules of gas in this container. Let's say you have n molecules in this container. That means, what is the total pressure going to be? The total pressure just now earlier we found mcx squared over L cube. The mc squared is actually the mass and the speed of the one particle. But if you got n particle, the mc squared, right? The c going to be all the particles up to n particle mc squared need to be added. So the equation going to turn to be like this. P is m over L cube, cx1, cx2, second particle, third particle until n particle. So this c1, c2, c3 all added become ncx squared. N number of particle n will be come out. Okay. So now the pressure caused by the n particle moving horizontally is same as the above, but just multiply by n. Nmcx squared over the L cube, right? L cube is actually the volume of the container. So we just put V, volume of the container. Okay, but this I forgot to tell you. You see, the symbol has been changed. You see, this is called this velocity is called min. This symbol is min square speed. This speed called is what? As min square speed. Min square speed. Okay. So you see cx1 squared, cx2 squared, cx3 squared. We just find the min of that speed, square speed. It's got to be min square speed. We average it out. Okay. Okay, just temporarily. What is meant by min square speed? Okay, let's say halfway we pit stop. We want to find what is meant by what is min square speed. Okay. For that, I go to this notes. I will guess. Scroll down. Okay. Here also we have that, of course, the kinetic theory, gas, the assumptions. Okay. Then the derivation also stated here. I just want to tell what is meant by mean square speed. Okay. See, one examples here. Okay. My focus. There are many types of speed. When come to particle speed. Let's say you have 7 molecules all traveling with the speed of 200, 300, 400, 500, 600, 700, and 800 meter per second. Okay, 7 speed for 7 variety of speed they are traveling. Okay, the first question: find the mean speed. Mean speed is easy. Just all of them add up, divide by 7, right? So you get 500. Okay, our focus is the second one. Mean square speed. So what is mean square speed? Mean square speed. It's called mean square speed. So what is mean square speed? Can you find mean square speed of these 7? Mean square speed means you square all the mean of the square of the speed. So 200 square, 300 square, 400 square, all add up to 800 square, divide by average of this. How many particles are there on top? 7. This is your mean square speed. Unit is what? Meter squared s negative 2. Okay, so this is called mean square speed. Just square the speed, the average of the square speed. It's called mean square speed. Okay, you have the third one, C, called root mean square speed. This I'll come back later. Okay, we hold on with C. So I just explained the B. It's called mean square speed. Square of the speed, the average of the square of the R speed. Yeah. So hope you got the idea. Okay, it's good. M squared S negative 2. Okay, so I go back to the slide. Okay, so this is called mean square speed. The square of the speed divided by the number of particles. So you got N here. Okay, this is the almost, we got the formula, pressure formula. But this pressure formula is pressure exerted to wall 1. Okay, wall 1. Okay, now we got one problem. The problem is the particle, not all particle moving horizontally, right? How you can say all particle moving horizontally? Some maybe move, not some, all of them moving might move randomly. Okay, they might move randomly, right? For example, okay, so this is the box. Okay, the particle moving randomly like 3D into the page, 3D into the page. That means if the speed is 2D, if this is the speed c, it has its horizontal component cx, will have its vertical component. Okay, if this c is coming out of the page, very difficult for me to draw the 3D. Let's say it's coming out of the page, it come out from the page. Okay, that means it will have another component cz, right? Like third component. Okay, 3D. Okay, so the particle in this box might move diagonally. It has these 3 components, cx, cy, cz, 3 components. Okay, how this cx, cy, cz connected to c? Let's say we don't go for cz first. Let's say 2D, only 2D. 2D, how c related to cx and cy? C squared equals to cx squared plus cz squared, right? Plus, sorry, 2D. If 3D means c is what? C squared is what? Cx squared plus cz squared plus, sorry, cy squared plus cz squared, right? This y earlier. Yeah, the 3 component squared should be c squared, right? For 3D. Okay. So, okay, I go back. Back to the slide. Okay. So the speed given here is only the horizontal component, but we want the formula in terms of c, the actual speed it's traveling. But you see this diagram, this formula, we know the c squared is equal to cx squared, cy squared, cz squared. All of them move diagonally. All of them have their 3 components. Okay. So can you write the cx squared in terms of c squared or not? Okay. So you see here, we agree c is cx squared, cy squared, cz squared. Okay. Okay. Since, okay, now there is one assumption, you see here, since there are large number of molecules, we can assume that there are equal number of moving in each of the coordinate direction. Or in other words, we can say that, do you agree if you have a box, the pressure at the phase 1, the pressure at the phase 2, the pressure at the top phase, got 6 phases, right? All 6 phases for a box will have same pressure or different pressure? Same pressure or different pressure? Let's say you heat up the box, contains a gas, a trapped gas. The box is going to become suddenly start to become a little bulge, right? It just a little, the phase started to come out, let's say, okay, phase comes out. The pressure in all surface, same or different? Same, right? The pressure exerted by the gas in all direction is same, right? So the pressure is same. That means in this three dimension, in x dimension, in x direction, x dimension, in the y dimension, in the y dimension vertically up, and the z dimension coming out from the page, in the all dimension, the pressure is the same. If the pressure same, that means the momentum, the total momentum change at this three dimension is the same. That means what they conclude is the Cx squared, Cy squared, Cz squared must be the same because pressure is same. Pressure in all directions same. Okay. So the Cx squared, Cy squared, Cz squared add up is C squared. But the Cx squared, Cy squared, Cz squared is the same. So the Cx, Cy, Cz is actually 3Cx squared. This conclude this. The Cs squared is actually 3Cx squared. Because pressure in all directions same. So we say equal number of particles, same number of particles move in this three dimension. Okay. If you have 900 particles, 300 particles move horizontally, 300 particles move vertically, 300 particles move coming out of the page to exert the same pressure throughout. Okay. That's why Cx, Cy, Cz must be the same. Okay. So Cx squared is actually 1/3 C squared, the actual speed. Actual mean square speed. So the formula turned out to become this. The Cx squared is just changed to mean C squared, average C squared. So this is the formula developed by scientists. Yeah, this formula is perfectly theoretical. Is from completely from theoretical. So you see the final formation. The P stands for the pressure on one of the surface. It depends to the number of particle. Do you agree, right? More N means more pressure. It depends to the mass of the particle. How massive is each particle here? Is it hydrogen? Is it helium? Helium will have more mass, so should exert more pressure. And now, speed, it depends to the pressure is found to be proportional to the mean square speed. Yeah, for the first time, we found a pressure formula in terms of speed. And this speed is something unique. This speed is called mean square speed. Okay, it's called mean square speed. And the pressure found to be inversely proportional to the volume. Okay. So this derivation you have to know from momentum, one particle. They find the changes in momentum. They find the force by the one particle. Then they make the model more elastic, go for n particle. Then they become more elastic, change the how the C squared related to Cx, Cy, Cz, and they got the equation. But I tell you, 2 or 3 times in the past year, only a part of this derivation has been asked. Part. Which part has been asked, 3 times? I think, if I'm mistaken, maybe three times. I think they are really focused to that. Which one? Okay, this part. From here. This region, towards the end. Okay, this part has been asked 3 times. How the Cx squared finally tend to become C squared, 1/3 C squared. This has been asked I think this is the most important part of the derivations you have to know. You have to say, however the molecule move in 3 dimensions. So the velocity of C is Cx squared, Cy squared, Cz squared. Because got large number of particles and the pressure in all direction is the same, 3 dimension is the same. Therefore, C squared is Cx squared, Cy squared, Cz squared must be the same. So C squared is 3Cx squared. So we get 1/3 C squared. We substitute. That's it. Okay, so make sure you remember this derivation towards the end. Any questions so far? Okay. So hope you got the idea. Okay, now let's move on. So from theoretical scientists, they said pressure is 1/3 nmc squared over V, where the n is number of particles or number of molecules. Small m is a mass of one molecule, and m is the total mass of the gas. V is the volume. And C, the highlight of this equation is the last term, mean square speed. Okay, average of the square speed. And 1 year, 2 marks question they ask from the top formula. Can you prove this equation? The below one 1/3 rho C squared. The Nm over V is actually the density of the gas. Okay. Nm is the total mass of the gas, and V is the volume of the gas. So mass over volume is actually the density of the gas. So P equals to 1/3 rho C squared. This is density of the gas. This means square speed. 2 marks question they ask in 1 year. From top, show the bottom. Okay. Okay, so we already done the main part of the topic. So on top of the O levels, you learn what? O levels, you learn PV is constant, P over T constant, V over T constant. Now all three combined, you get PV equals to nRT, PV equals to nKT, and P1 V1 over T1 equals to P2 V2 over T2. This is what you learn in A levels now. But on top of that, from kinetic theory, we found this the new addition in this list. The pressure is, if I bring the volume the other side, volume the other side, so PV equals to 1/3 nmc squared. Purely theoretical. Okay, now you can ask, what is the use of this derivation? Why we need to learn this in A levels? What is use for us? This derivation. We are quite okay with PV equals to nRT and PV equals to nKT. Okay. Any volume, any pressure, we can find the temperature by using this formula. So what is the use of this new formula? Actually, this new formula does a very important contribution. What is the contribution? This formula towards the end gives us the kinetic energy formula for a molecule. Okay. You know, kinetic energy of a particle is, we know, is half mc squared, half mv squared. I think beginning of the topic I told you. So if you are sitting in a room, if I ask, okay, there is lots of oxygen particles in your room in front of you. If I ask, what is the kinetic energy that oxygen particle possess now? Very difficult for you to calculate because you need to know the mass of the oxygen. That's okay. It's in your periodic table. You can find the mass. But you don't know what speed the oxygen in front of you are traveling. It's very difficult to measure that speed. But this formula just now, the one we derived just now, can help us to get another kinetic energy formula. Okay. So this is the derivation. First, from the from the what do you call, from the theory, PV is 1/3 nmc squared. From the equation of state, PV equals to nkt. We know nkt is confirmed correct, 100% is correct. It has been proven through experiment. The above equation theoretically accepted. Okay, theoretically accepted. Okay. So if these two correct, so therefore 1/3 nmc squared must be same as nkt, right? From here, they try to find the kinetic energy formula. The n they cancel. Okay. You get what? You get 1/3 mc squared. Get 1/3 mc squared. So 1/3 lah, 1/3. So this 1/3, okay, the 1/3, they try to write like this: 2/3 times 1 half. Actually, let me, maybe this part confusing you. Okay, let me show you. So PV equals to 1/3 nm c squared. Okay. PV equals to nkt. So 1/3 nm c squared is equals to nkt. So n cancel. So 1/3 mc squared nkt. Okay. You want to find kinetic energy formula. Kinetic energy is half mc squared. You want to get half, not 1/3 here. So how do you change 1/3 to half? You want to create here half. You want to create here inside half mc squared. But it's actually 1/3. Okay. What times r will tend to become 1/3? X times half is equals to 1/3. So what is x? This actually outside here is x. What is x? It's 203, right? X is 203. So it's 203, right? Outside is 203. 203 times r is 1/3, right? Why we do this? Here the n cancel. It's going to left with kt. Yeah, why we do this? We want to find the half mc squared. Okay. So this is the kinetic energy of the particle is equals to 3/2. 2/3. Bring the other side is 3/2 kt. Yeah. This is the one of the biggest discovery in theoretical scientists. They found kinetic energy formula. One particle is they found is 3/2 kt. 3/2 constant. K is a Boltzmann constant, and T is what? Thermodynamic temperature. Thermodynamic temperature. Thermodynamic temperature means temperature in Kelvin. Yeah. So if I ask you now, you are having class, front of you got lots of oxygen, hydrogen molecules. Okay, I'm asking, what is the energy, kinetic energy possessed by one oxygen particle in your room? Do you need to know the speed? No. The kinetic energy is just 3/2 kt. So what you need to measure now? You want to find the kinetic energy of the particle? Just take a thermometer, measure the room temperature. That's all. See, the room temperature gives you 27 degrees Celsius. The kinetic energy possessed by one oxygen particle is 3/2 K times 27 plus 273.15 Kelvin. So whatever you got in Joule. So this is the kinetic energy possessed by the oxygen particle. Okay. So the is it something easy for us? Yeah, they make easy for us to find the kinetic energy of a particle. Just need to know the temperature. That's all. Okay. No need to find the speed. We don't know how to find the speed also. How are you going to find the speed of the particle moving from one point to another? We can't even see the oxygen particle naked eye. How are you going to measure the speed? But this formula really helps us to find the kinetic energy. Okay. So you know the temperature, you should be able to find the kinetic energy of one particle. Okay. But the scientists work the other way around. They get the kinetic energy. From the kinetic energy, they calculate what speed the oxygen is traveling. They work the other way around. They get that They get the kinetic energy first, 3 over 2 kT. From there, they predicted what speed the oxygen particle is traveling now. Okay. Yeah. So that's the last part of this topic. Actually, we are almost done with the topic. So 1/3 nmc squared nkt. So the kinetic energy of the particle is found to be 3 over 2 kT. So kinetic energy of the particle is directly proportional to temperature, has been proven. I don't know you believe or not. Last time in your O levels, people said when the temperature of the gas rises, the kinetic energy of the gas rises. What is the proof? This is the proof. The kinetic energy is found to be proportional to temperature. What is the proof? This equation is the proof. 3 over 2 kT. Okay, now you learn the proof. Okay, and this temperature is called thermodynamic temperature, or you can say absolute temperature. I've got two names now: thermodynamic temperature or absolute temperature, measured in Kelvin. Okay. The internal energy, this part we will be discussing this in the next topic. For time being, just understand about the kinetic energy first. Okay. So this is the summary. We are almost done. Now we need to strengthen the idea by doing some questions. So this is a summary what you learn. Okay. The equation of state PV, nRT, PV, and KT. The pressure of gas from the theoretical, we found P is 1/3 nmc squared and P is 1/3 rho c squared. By comparing the what do you call the PV equals to nkt with the theoretical equation, the big discovery is kinetic energy of a particle is discovered. 3 over 2 kT is the highlight of the topic. Okay. So yeah, what all the symbols represents is here. Another highlight, of course, don't forget this speed is called what? Mean square speed. Okay, mean square speed. Okay, before we continue with this, okay, so I'm just focusing to the final discovery. Kinetic energy of a particle is 3 over 2 kT. Most of the students get confused. This is the kinetic energy of the entire gas. No, just kinetic energy of one particle. One particle. Let's say you have a container. And let's say this container has n mole of particle. So what is the total kinetic energy the particle has? 3 over 2 kT times with n. You have to multiply by n. Okay. If the gas contains with 2 mole of gas at temperature of 27 degrees Celsius, what is the total kinetic energy of the particle? Same. Kinetic energy is 3 over 2 kT multiplied by the cos n, the number of particles. In this case, if 2 mole means how much of number of particle it possesses, multiplied by 2Na, right? 2Na, 2Na, correct? Yeah. So you get the total kinetic energy in Joule. Okay. So remember 3 over 2 kT is kinetic energy of one particle, only for one particle. Okay. Now tell me, you are having class now, okay? You have oxygen, gas, you have a what do you call, not hydrogen, can't be hydrogen in your room. You have oxygen, let's say you have a carbon dioxide here, okay? Yeah, you have nitrogen, you have all three type of gases, okay? Tell me, all these three gases exposed to the same temperature, all of them exposed to the same temperature. Tell me, all of them have different mass, okay? Do all of them have same kinetic energy or different kinetic energy? If they exposed to the same temperature, they have same kinetic energy or different kinetic energy? Should be same, right? Because kinetic energy is 3 over 2 kT. The kinetic energy looks like the formula. It nothing to do with the mass. It just depends to the temperature. So in your room now, the oxygen, nitrogen, carbon dioxide, all of them have the same kinetic energy. All of them have the same kinetic energy. But what is different? The more massive one, of course, the carbon dioxide is very massive. More massive particle will have a small speed, will have a small velocity, small speed, like travel slowly. But their kinetic energy is the same. The kinetic energy is only the only factor affects the kinetic energy is the absolute temperature or thermodynamic temperature of the room. That's all. Okay. Any questions? Okay, no questions. Okay, another one. The 3/2 kT, of course, is same as half mv squared. Okay, half mv squared. 3/2 kT half m. This v is actually we write as mean square speed. This v squared is actually mean square speed. It's a mean average speed. At one particle temperature, the particle move in a range of speed. So we need to find the average speed as a mean square speed. This kinetic energy, I forgot to say, this is average kinetic energy. You need to use the word average. It's average kinetic energy of the particle. Okay, so this is the mean square speed. So now, as I said, if you know the kinetic energy, you can work out the mean square speed of the particle. Okay, the mean square speed of the particle. So remember, the mean square speed is actually directly proportional to the kinetic energy of the particle. Which speed proportional to the kinetic energy of the particle? The mean square speed. Okay, the mean square speed is the one proportional to the kinetic energy of the particle. Okay, yeah. So a particle which has a greater mass will have a smaller mean square speed. They will possess the same kinetic energy for the same temperature. Okay. Okay. So lots of new ideas. Lots of new ideas. I don't want to extend further. The next class we will explore the question tomorrow morning. How it works. So, sorry, not this one. That's it. Okay, so what you learned today? You learn about kinetic theory of gases. Remember at least 3. Okay, then pressure formula based on kinetic theory was derived. You end up getting PV equals to 1/3 nmc squared. And we got changed the nm over v as the density. It's got mean square speed. Then finally, kinetic energy of a molecule has been derived. PV equals nkt 1/3 nmc squared compared. We got the kinetic energy of one particle is found to be 3/2 kT. Okay. So yeah, so that's all. So next class we'll be discussing these questions. Okay. Homework. It's okay. This one we tried in our class tomorrow. Okay. As the background, as usual, focus to AS first. To your trial papers. Okay. Okay. Any questions? I know you have lots of questions. You only have lots of questions when you tried these questions. Okay. So the next class, we strengthen this idea. Okay. Okay. So I stop here. Thanks. So those who have questions, you can stay back. Those who don't have, you can leave.